In this video, we're going to do some examples of rewriting expressions using logical operators and conditional and biconditional statements. So first, I'd like you to take a look at the four expressions below and rewrite those using the symbols and, or, and not as appropriate. So take a look at those, pause the video, try those out, grab a piece of paper, and then we'll talk about it together. Okay, the first, X is an element of A intersected with B. So this means that X is in A and X is in B. So X is in A and X is in B. That's what X being in the intersection of A and B means. And so when we want to rewrite this using our logical operators, one way that we could write that is X is an element of A and, logical operator for and, X is an element of B. And if we want, we could put parentheses around these. It's not absolutely necessary, but this is the kind of thing I'm looking for. A quick note of something that is not what we want to write would be something like X is in A and B, where again, this is the symbol for and. So and, the logical operator and, should separate things that are sort of complete phrases. X is an element of A and X is an element of B. X is an element of A and B. We might say that. What we really mean is the intersection. X is an element of A and X is an element of B. So this is not the way that we use and, because we want to separate complete phrases like this is good, versus just set symbols or sets. All right, X is an element of A minus B, or the difference between A and B. So there's a couple ways that we could write this. One way we could write this is to say that X is an element of A and X is not an element of B. That would be one way that we could write that using and. We could also write this as X is an element of A and it is not the case that X is an element of B. So there we're using both and as well as not. That would be another way we could write it. We could also write X is an element of A and X is an element of B complement. So those would all be ways that we could rewrite that statement using our symbols here. And not would be appropriate symbols to use. At least one of the sets A and B is finite. At least one of them means that A is finite or B is finite or both are finite. So A or B or both is what at least one means, right? And therefore that's or, that's union. And so that would be A is finite. We could write that as the cardinality of A is less than infinity, or the cardinality of B is less than infinity. So that's how we could write that statement using or. X is a rational number, but Y is not. So logically, this is saying X is a rational number, and it is also the case that Y is not a rational number. So one way we could write this is X is an element of Q, the rational numbers, and it is not the case that Y is an element of Q, the rational numbers. Another way we could write that is say X is an element of the rational numbers and Y is not an element of Q, the rational numbers. So we could either use not an element of, or we could use the symbol for not. For the next set of problems, I'd like you to rewrite them of the form either if P then Q, or P if and only if Q. So you can use this notation, or you can also use this notation. So if P then Q, P implies Q. P if and only if Q, that's a double arrow. P implies Q, and Q implies P. So I'd like you to take a look at these sentences below. A graph has an even number of edges whenever it has an odd number of vertices. To pass a course, it is necessary and sufficient that your final average is above 59.5%. For guacamole to be good, it is sufficient that it has cilantro. For guacamole to be good, it is necessary that it has cilantro. A number x is rational exactly when x over 4 is rational. Aaron will eat a fruit only if the fruit is an apple. Aaron will eat a fruit if the fruit is an apple. And if x is even, then it is an integer multiple of 2. And if x is an integer multiple of 2, then it is even. So pause, try these out, rewriting them in one of the forms above, and we'll talk about them together. Okay, a graph has an even number of edges whenever it has an odd number of vertices. So that means when this happens, this must happen too. So when it has an odd number of vertices, the graph will have an even number of edges. That is, if graph has odd number of vertices, then has an even number of edges. So I'm abbreviating a little bit. So if a graph has an odd number of vertices, then the graph has an even number of edges. So in other words, this is our P and this is our Q. And so we're writing something of the form P implies Q. To pass a course, it is necessary and sufficient that your final average is above 59.5%. Necessary and sufficient means going in both directions. So pass course if and only if average above 59.5%. So that's an if and only if, a biconditional statement. For guacamole to be good, it is sufficient that it has cilantro. This is saying as long as it has cilantro, then it will be good. So having cilantro, it is sufficient to have cilantro to be good. So in other words, this is guac has cilantro implies guac is good. Whereas necessary, that's going the reverse way. For guacamole to be good, it is necessary that it has cilantro. In other words, if the guacamole was good, it must be the case that it has cilantro. So guacamole being good means that it must have cilantro. Next, a number x is irrational exactly when x over 4 is irrational. Exactly when, that's an if and only if situation. So exactly when this happens, and exactly when this happens, if and only if. So x is irrational is not an element of the rational numbers. If and only if x over 4 is not an element of the rational numbers. Aaron will eat a fruit only if the fruit is an apple. So if Aaron eats the fruit, then the fruit must have been an apple. Aaron will eat a fruit only if it is an apple. If it's anything else, he will not eat it. And so Aaron will eat the fruit implies the fruit is an apple. Aaron will eat the fruit if the fruit is an apple. If P, then Q. If the fruit is an apple, then Aaron will eat it. So those are those two pieces of if and only if. Remember that our double arrow is, P implies Q and Q implies P. The only if is P implies Q. The if is Q implies P. Lastly, if x is even, then x is an integer multiple of 2. And if x is an integer multiple of 2, then it is even. So this is a long way of saying that this is an if and only if statement. If P holds, then Q holds, and if Q holds, then P holds. So in other words, X is even if and only if X is an integer multiple of 2.